now. So, hello everyone. In this less formal session, we will start prototyping an exhaustiveness checking / pattern matching algorithm that we might use in Draco eventually. This will be a bit less planned out as the usual streams. We won't be working on the compiler directly. We're going to be toying in a different project, doing a minimal viable example of the algorithm that we want to examine, and we're only going to familiarize ourselves with the concepts of this algorithm. So, I have an empty project here. I also have Draco open, but we won't need that. I'll just close that. And we're going to implement something fairly minimal here, just as a proof of concept, and if it works, we understand it well, we like it, then we're going to probably use it in the compiler. Now, as usual, I've prepared a small markdown document here. I've only listed two things here, the blog post and the paper that I'll essentially reference. I would love to open this in Markdown for you, but my Visual Studio just decided today that when I closed it, it decided to reinstall itself, and the uninstall process went fine, but reinstalling didn't, so half of my extensions are broken and not set up properly, so I'm sorry for this. I'll also have these two open on a separate tab here. I'll show you both. So this is the blog post. It's a high-level overview of the algorithm. This is mainly what I've read for a quick recap. And this is the beautiful paper itself, which is, the same thing, more formally, and publicized in publicized somewhere. I'm not sure. Oh, it's in J, functional programming. Okay. So, in high-level terms, this pattern matching algorithm works by constructing a matrix from the match construct. Now, here's an example. So, if this is your match expression, then you'll have you'll have three matrices. Or rather a matrix and two vectors. So one row vector will represent the input tuple in case there are multiple inputs. And the matrix on the bottom here represents the rows or arms of the match expression, each representing the corresponding pattern. As you can see, the first row is a nil discard, so the first row of the matrix is nil discard, the second row is discard nil, just as in the matrix, and the third row is subpatterns, so that's what we have here. And on the right side, for each corresponding match arm, or rather the left side of the match arm, we assign an action or the expression in the compiler that you would assign to that pattern. For us, this isn't really an important part. We'll also keep these as numbers or strings or whatever we want in our prototype. We are only concerned with checking what's in the matrix here. Now, the goal of this algorithm is to construct a decision tree that tries to efficiently guess which pattern fits this given tuple of values. And it also gives you a way to detect if an arm is useless. For example, if it's already been covered by a previous arm. As an example, I could try to write something here. Draco won't work, obviously, as a highlighting. But if you have something like a discard, then you have a 1-1. Then obviously the discard pattern already covers the 1-1. So this one would be a useless arm. and it will also detect if you didn't cover all of the values. That's the other thing. So that one refers to what we refer to as exhaustiveness checking as outsiders. So how does this algorithm work? Well, it's pretty nicely detailed here. It might be a bit too formal for an average programmer. It's a bit too formal for me as well. I'm not used to reading these kinds of papers anymore. I used to implement some of these algorithms from things like the Dragon book when I studied parsers, but it's been quite a long time. Well, hopefully this one will go well. The gist is that we are specifying some operations, for example, how you specialize the matrix for one of the variants in the discriminated union. There's also the operation of defaulting, the remaining set of arms here, and there's also an operation called swapping, which is the simplest one. It just swaps the columns of the matrix, and the inputs are swapped alongside, so that one is dragged alongside with it. And here's the algorithm in detail. We'll read more about this in a bit. It's essentially a recursive algorithm trying to dissect different parts of the matrix that we have in the middle. So let's try to lay out a little framework for this algorithm. And what I thought is that we could model the bare essentials that we would need for this algorithm. For that we could model abstract data types or discriminated unions. For type theorist people, I'm just going to call these ADTs. So this will be a single abstract data type. It will have a name. I don't think we even need a name for it. We just need to store the type constructor names. We won't even bother storing things like the number of parameters because that's more of a type checking thing. This algorithm will only bother doing the exhaustiveness check and such. So for that, an ADT can store only the type constructor names, I suppose. So we could have a private read-only member. It could be a hash set of names. And we could do something nice and make this kind of a DSL-like thingy by implementing IEnumerable and then adding an add method here. And then let's implement it through this member. Let's clean this up a little. And with that, we can do something like this, which is kind of nice. So if you don't know what we're modeling here, let me just write an example. For example, the maybe type will be modeled in this program as such. So it has two type constructors, or two variants if you like. One is called sum, one is called none, which is roughly equivalent to, for example, this example. So we have a sum constructor that takes two parameters, and then we have a none constructor that takes no parameters at all. So for our case, we won't really deal with the number of parameters. It will be sort of assumed that it's always correct, because it's, again, not the gist of this algorithm, so to say. And we also won't have things like constants. We will actually just model them through ADTs. So for example, the integer type, we'll be able to just model like so. Let's go up until like 5. And that should be it. That's that's kind of enough for us in terms of ADTs. Now, the next thing that we need to be able to model is a match construct that we want to check with this algorithm. And for that, we are going to obviously need to model patterns. And we already do that in the language, sort of, but we will have a simplified version of them. So what I thought is that you could use patterns, and we're going to use this nested style that kind of emulates how you would nest DU variants in a language that actually has DUs. So we will have only two kinds of patterns. One will be discard, and the other one will be a type constructor. And the type constructor will store what's the abstract data type that it originates from. It will store the constructor name, and it will have to store the sub patterns that it's deconstructing its members into. Let's call this arguments, maybe. So the next thing that we want to be able to model is the match itself, which will obviously have match arms. This is kind of similar to how we stored in the compiler as well. And on the left side of the arm, we will have a list of patterns, or we could just have a single pattern. That's what I'm wondering about. If you want to model the top level match as always a singular construct, but since we likely won't do that, like in the compiler, we'll just allow you to list a bunch of values here. What I'm thinking is that we could allow multiple patterns on the left side of the arm already. And on the right side, we want to have a so-called action that the blog post called it an action, which is on the right side of these arrows. We're just gonna call them. We're just gonna model them as strings for now. Again, this is not important. This would be only important if we are planning to visualize them, and for visualization, a string is perfectly fine. So the next thing that we're going to model is going to be the match expression itself, and we're going to do some DSL-like thingy here as well. So it will need the parameters that you pass into the match, and we're just going to store it as a list of strings. For example, this would be the string X and the string Y in a list. And I suppose we can call it arguments. And we're going to store the arms of the match. And we're going to create a constructor. Well, I kind of don't want to do this. Let's make another DSL-like thing where we can use the braces to initialize the arms of the match. So what we can do is make this a private read-only. I forgot an E, and it can be just a list. Can make this an I enumerable, or rather we could make it an I read-only list of match arms, and we can implement it through arms. That's fine. Let's clean it up a little. And in the constructor we could do something like take the name of the arguments as params. don't want to make this solution any efficient. We want it to look nice and easy to copy into the real-world compiler once we're done with it. And since we made this an enumerable, we can do something like public void add. And we can essentially just ask for patterns, a pair of pattern and action. And what I'm thinking is that I might just want to take a single pattern here for now. And with that, we should be able to write something like new match. And let's try to imitate this example, this one, because I think that there will be a tree. Oh no, let's do this one, because there's even a decision tree already written out nicely like this. There are more complex examples later on, but let's stick to this one. It's nice and small. So we have a maybe type with some none, and we're passing in a value called v. We model it as just passing v here, and then in braces we can just specify the arms. So first we have a sum, which is a constructor pattern. And the ADT is the maybe type. The name is going to be sum, and the sub patterns is let me cheat. It's gonna be 1 and x, which is the 1 if we model by again a constructor pattern. And it's going to be an int type, and the name is going to be 1. It has no arguments. And the second argument to this sum is actually a discard. Well, it's a bound name here, but in reality this isn't very different from just discarding the value, because it literally can match everything. Now, as you can see, this is quite cumbersome to write, and it also doesn't like to infer the immutable array type here. What did I screw up? Oh, we need an action on the right side, so I think this is called action 1. Yes, as you can see, this is action 1. You can see that this is quite ugly to write, so we're going to write a couple of utility functions to make the construction of samples a bit nicer. For example, we can do something like a construct here in the ADT type itself, and here we can take the name of the constructor, and we can also take a params pattern arguments, and we can do some nice utility that if the constructor names doesn't contain this name, then we can throw away an argument out of range exception. Otherwise, we can just construct the pattern for the user. This is almost good. Okay, with this it should already be quite a bit shorter, because this construction can just become this. this one can become this, and for the discard we could just introduce a local constant or something. That's nice. Okay, this is already way nicer. It's a bit more readable that we're constructing a sum value with the value 1 and a discard. This is the pattern, and we're assigning the action 1 to this arm. Now the second one, the second arm, is this. The first value is a discard, the second is a constant of 2, and it's assigning it to action 2. So let's do that. First we have a discard, then we have a constructor with a 2, and this is the second action, and the last action is actually just none, and that takes no parameters, and this is assigned the action 3. So this is going to be this sort of AST for our match expression that we're going to check with this algorithm. We could maybe even do something nicer and factor these out, but we're not going to do that. This is readable enough, at least for now. So now we have modeled match, pattern, and the ADTs. I think we have modeled everything that we need for the inputs of the algorithm. So now let's try to start understanding the algorithm itself. So let's start from the beginning and look what we need to go through. So the construction of the initial matrix is not too difficult. We essentially take the inputs and we take the match arms. So we take the entire match expression, and from that we can construct the row matrix by the input parameters. This big matrix down here by taking the left sides of the match arms, and the column vector here of actions by taking the right hand side of the match arms. So I suppose that this is going to represent a single node in the tree somewhere later in the algorithm. So if you saw this decision tree thingy, it's always dissecting these matrices into something bigger or something smaller and more elaborate, I suppose. So we could model this triplet of 2 vectors and a matrix in a class called a node, maybe a decision tree node or something. Now what I'm noticing is that the algorithm is also assuming that that the input is there is only one input. At least this example does, and the way we modeled the match arm, we should do that as well. So let's just call this an argument and expect a singular one. Later we can always make this a list or something if you need to, but I think it's simpler to first think of the basic case, you know, just passing in a singular value like we do here. Later on we will naturally see how we can expand this to passing in a tuple of values, or maybe it turns out we don't even need it because we can just model it as a constructor right away. So let's go back to how the algorithm works. So we have discussed construction. let's actually try to implement that. So we're going to model a decision tree node. And this is going to contain a triplet of a row vector. I'm just going to leave it as an array for now. I don't think that we need to mutate this. It would be very unwise to mutate it, because while constructing the tree, if we copy it by reference somewhere, we can just mess up the parents. So in that case, let's just leave it as an immutable array. That's even safer. And this is going to be the inputs, or rather arguments, as we call them so far. So this is going to be this top row vector. Then we're going to have a matrix here, and this obviously has to be a 2D matrix. And I know that C# does have multi-dimensional arrays, but they do not have nice operations like taking a certain row, column, or submatrix. So for us, it won't really matter, and I'm just going to implement it as an immutable array of immutable arrays. And this is going to contain the patterns. And this is going to be row major, I believe. So each element in this outer array will be a row, and each element within a row's array will be one pattern in that row. And the last thing that we need to model is this column vector, which is the action table, or action vector rather. And I believe we can just generate a constructor that takes all these. Okay. We might also want to take the parent node. So this is going to be a single node in this tree that we are constructing here. I keep scrolling back to this example, sorry guys. But with this, I believe that we have successfully implemented the data structure of this algorithm that it needs. So let's start with the simplest operation, which is construction. Let's actually make this a private constructor, and I'll expose whatever needs to be exposed through public static methods. So I'll keep the naming conventions of this blog post. So construction will be the thing that takes our match expression, and we'll construct the root node. And the parent node will be null, as this will be the root of the node. The arguments, there is only a single one in the beginning. If you see the example, there's just one, and we can take this as the matches argument, and we need to wrap that in an immutable array. Now the patterns will be more interesting, as the match has it in a different construct than we do, but we have the power of link. So we'll do something like, for each arm, we just take the patterns on the pattern on the left, and that's singular pattern. Okay. We have a singular pattern here, which is not correct. We need a list of patterns here, as these sum, for example, can be exploded into a 2x2 matrix. So one pattern on the left side of an arm is obviously not enough. Well, in the beginning it can be, because we just agreed, sort of. Sorry, I agreed with myself, guys. You had no saying in this. But in the beginning, every element is just a singular thing here, and once we explode sum, for example, which will be an operation called specialization, that will have a wider matrix. So what I'm going to do is wrap this in an array. And the result of this can be wrapped in an immutable array as well, or rather converted to an immutable array. And this should be, yep, a nested immutable array of patterns. And finally we need the column vector of actions, and that's actually pretty simple. We can just take the arms of each match, and we can just select the action from the right side. And that should be it. We have the root decision tree node. Oops, that's not what I meant to do. For shits and giggles, let's try to actually print this. Well, we won't print this because this is just a class, we'll just print the type, but let's inspect it through the debugger. So let's call what we have, and let's see what we created from it. Okay, let's see what node is. So we have 3 actions, just as expected. This one was pretty easy. We have a single argument v, and as for the patterns, it's 3 rows. It's a 3 by 1 matrix, and it has everything correctly. I believe it's a bit harder to read. We can actually do something about this and override the toString for patterns. Maybe that will come in handy. So we do something like this. Whoops, this isn't the right syntax for it. Okay, we might beautify this a little by saying that if the number of arguments is 0, then we just print the name, and otherwise we print the parenthesized arguments. Okay, and we can actually beautify match arms too, but they're not present in the node itself, so we'll just leave that as is. So let's see now in node what we have in patterns. So the first row is a sum of 1 and anything, and that is correct. And the second row is a sum of anything and 2, and that's correct as well. And the third row should be a none, and that's correct as well. Okay, so we have successfully implemented the first step of this algorithm, which is constructing the root triplet from the match expression. Now, this was the simplest operation, so let's move on. The next one is called specialization, which is a bit more interesting, and this one is actually related to matching. Finally, so what specialization is saying that For example, let's collect out all the members here that has sum on the constructor in the first column, because we can assume that there are multiple columns in this matrix. And let's take their arguments and construct a submatrix of it, and keep the corresponding actions, and keep track of how we transformed the path from the root argument that we matched. So since this is this column represents the first element in the sum constructor, it would be indexed as accessing v.0, and the second column, which is the next element, the second element in the sum constructor, it's indexed as v.1. So this is what we're going to do next, implement this specialization construct. Now, specialization can be a constructor or a constructor name or any constant value, but we simplified our case here by only having constructors. So let's implement this algorithm. I'm just going to have it as a public decision tree node specialize. Or did it call it specialization? Let's do it specialization. I know these are not verbs, so they shouldn't be method names, but I call this one construction with array, so I'm already screwed. So we're going to take the constructor name, and I believe that's all we should actually need here. So what we're going to do is, if you can notice that this operation only filters rows, so it doesn't filter columns. And since we have rows in the outer array of these patterns, it's pretty simple to implement. So we're going to construct a few immutable arrays to keep track of immutable array builders that we're going to store our results in. Now we will have a remaining pattern rows, or just remaining patterns. And since the actions correspond to the rows, we'll have a remaining actions builder as well. And this will just take strings. Now I'll go through each row by index. And what matters here, you will see later in the algorithm, is that the first column of the given row matches this constructor name. So I'll pick out the row like this to have a nicer name. And now we will check if the row is a constructor pattern where the name matches this. Is this legal C# even? We'll do the first element of the... Ah, almost. We were close. This is a already occupied name. Let's call this ctor name. If this is the case, then the first column matched whatever we wanted to specialize to. So we will need to add this to the result. Once we're done, then we can actually go ahead and construct a new decision tree node. Now the parent of this one is very simply going to be this, probably. We'll see later in the algorithm when we run it. As for the arguments, now this is the first interesting thing. When we deconstruct, then we take the argument, the first element of the arguments of the old node, and we have to split it apart into the constructor elements of whatever we specialize to. So we take the first argument, and we actually need to somehow generate for each element, and I wonder how we can do that. Well, we could take the first element and cast it to a type constructor and check how many elements it has. But what if the remaining patterns is empty? I don't think that's possible. I think we will always have remaining patterns here. So what we could do is do something like this argc as for arc count. This is a pretty lengthy line, and it's not even correct. And this is because we didn't index it twice. This should be correct. And now we can do something like enumerable dot range. And what we're going to do is sort of try to follow the pattern that the paper does here. So we're going to put the first argument into square brackets. And then we're just going to append the index after a dot, just like here. And after that, it's important to concatenate it with the rest of the arguments, of course. And we're going to turn this into an immutable array. Again, this isn't too efficient. In a real compiler, you would probably keep track of how to access these or the bindings to the sub patterns, or again expressions, how you would access these sub patterns. But I guess compiling them like with these string representations can sort of be similar. As for patterns, we just have this in remaining patterns. For actions, we have the remaining actions array here. So let's actually try this out and see if this works. So we're going to call specialization on node, and we're going to pass in sum, as this example specializes on sum that results in this triplet of matrices, or whatever I should call them. Okay, we didn't crash anywhere, that's good. And we have two actions and two arguments, that's good. So actions 1 and 2, and that's correct. We dropped the last row. We should be having v.0 and v.1 as the arguments, and that is correct. And we should be having 1x or 1 discard and then discard 2 in the second row. So let's take a look at that. This is one discard. Oh, we didn't unwrap the pattern. Okay, we need to do that. And we need discard 2. So what we forgot to do here is, if this is a constructor, then in the remaining patterns we obviously need to do the same kind of splatting as we did with the arguments. So we already have the first pattern bound here as a constructor, so we can just take the arguments of this, we concatenate with it with the remainder of the row, and we turn it into an immutable array. Let's try it again like this. So now, in patterns, we have 1 and discard, and in the second row we have discard and 2, which is perfect. So I believe we have created the gist of specialization. Now I think there is a note here that if we specialize none, we should have a single element in that matrix still. So let's see what happens here when we specialize none. We actually have an index out of range. And this is because there are no patterns in this single row. It's a null array. And what the algorithm is telling us is that for consistency, null array constructors such as none must be treated as though they carry unit. So we need to essentially have a discard pattern injected into them here. So what we can do here is have a ternary, and for the empty case, we're just going to have 1 here. Now I do wonder if we covered that here actually. I don't think we did. So I think what we need to do is that if the number of arguments is 0, then we're just going to create an empty, well, not an empty, but a singular one that actually just discards. Let's try it again and specialize to none. Almost. What did we screw up this time? Oh wait, I did a cast here. That's the problem. Was it the same problem before? Oh, I know why. Because now we actually don't have an empty remaining patterns list here. So what we actually need to check if that the length is, oh, we can do something like is Larry. I believe this should solve it. It's a bit dirty. So, for none, we only have the action 3, which is correct, and we should have a single pattern remaining, which is the discard. Now let's check again for specializing to sum. Let's see if we screwed up anything while we implemented null arrays. So we should have the actions 1 and 2 remaining, that's correct. The inputs are v.0 and v.1. And that is not correct at all. We lost the arguments somewhere. Why did we lose the arguments? Let's try to stop the algorithm here. So it's not null array. Oh, of course, because we deconstructed them. So, and then it's just taking the first element and assuming that's a constructor which isn't even correct by any means. So what we could do instead is actually take a constructor pattern here. And here we can say that we need the same name as this pattern. And we don't need to check if something's null array. What we can do here is, if the pattern.arguments.length is 0, we can do this special casing, and we can actually paste the note here. Oops, that's the wrong key. I'll just leave this in here for myself or anyone else who wants to read through this example later. It will also be easier to search back from the blog post to see what corresponds to what. This is useless, and what we can do is and this just actually became a max function. So let's try one more time. Obviously this won't work this time, but we can just change this to something like this. We could have also passed in the name of the pattern or the name of the constructor and the number of arguments, but I believe this is simpler. And of course you do not return a constructor pattern, but we can solve that. Okay, now let's try, hopefully for the last time, to specialize sum. Now the actions are 1 and 2, we know that's correct. Arguments are v.0 and v.1, that's also correct. And the patterns should be 1 discard and then discard 2. 1 discard and discard 2, this is correct. And now let's try to specialize none. And for that, we only have the action 3, that's correct. The arguments is v.0. Well, it should have been just v. But you know, it doesn't really matter. This is a nuller. We won't really care about this case. And we only care about that this matrix is not empty. And indeed it's not. So awesome. Let's move on. This operation was the first interesting one, but it's certainly not the hardest one, because now we get to defaulting. And this is where we start to do things like checking if some checks are redundant, something's not covered. So in a sense, this is where we can detect two things: if something's already covered in this submatrix, and if something's not covered. For example, if not all 8-bit values or 8-bit integers are covered in a pattern match that matches 8-bit values, for example. So let's try to read through this and refresh my mind. So producing the default matrix of a given pattern matrix retains only the rows that match constructors or values not already present in the column being scrutinized. I hope I pronounced that right. In other words, if the column being scrutinized contains an irrefutable either a pattern variable or wildcard entry. So let me translate this for you: a pattern that matches everything, then its decomposition is included in the default matrix. Or in the case where matching is inexhaustive, defaulting creates an empty pattern matrix, since there are no rows to admit any constructor or value. Intuitively, if each interior node of the decision tree switches on a column's value using the occurrence for that column, then defaulting is used to create the default case to account for constructors or values not present. Okay, so we have two things here. One, we need to see if we have any redundancy. So if we examine the first column and we find something that's a variable or wildcard, then we include it in the default matrix. Or if we only find constants and not everything is covered, then, or constructors and not everything is covered, then we need to add a default case for that. So let's try to implement this operation. This will work by picking a column, and I believe that we can always just pick the first column, but for safety I'll just take it in as a parameter. And again, I'm just going to copy the title of the paragraph here to make it easier to match up with what we're implementing. And I won't actually use that name scrutinized or whatever that cursed word is. I'm just going to call it, well, let's call it observed column. So first off, we need a way to check if something is exhaustive or not, and we could introduce something, a property for the patterns. But since there are only two, we don't need to. I was thinking we could do something like public abstract bool matches everything, but since we only have two, we can just check if anything is discard, and if it is, then it just matches everything automatically. We might still do that though, because in a real world scenario, you don't only have these two patterns, so you have things like constants as well, or even bound names. So discard matches everything, and the constructor doesn't match everything by itself. So Sorry if you guys hear any noises from the outside. We're in an apartment building and kids like to run around. Shouting, of course. So this looks like this operation again is just filtering on rows. So I'll just copy this start for us, and well, I will even steal this. Maybe we don't need to. I think first we'll have to check if we are containing an irrefutable value in this column before doing anything else. So, yeah. Well, instead of contains, we could use has. And what we could do is go through the given column. And what we could check if that in the given row. Well, this was stupid. We could have just said this dot pattern, since this is row major dot any. That matches everything. So, if this is the case, then the decomposition of it is included in the default matrix. And what I believe here is that the non-irrefutable rows can be discarded. So now we could actually go through each row and I think a for each is fine here because no, for each is not fine because we're also tracking actions, of course. So if we have an irrefutable value and this row's observed column is an irrefutable value, we include it. Just a second, I'll take a sip. We can add the corresponding action. We could even include the text that the blog is specifying here. Otherwise, if this is not an irrefutable value and this column has no irrefutable value, then we know that this is a constant, or rather a constructor pattern, or constant, it could be either. And we need to check if this has already been covered. Now I believe we need a set for that. And I'm just going to shove in the constructor names here. Now I believe it's safe here to cast to a constructor pattern, since otherwise we would have an irrefutable pattern in the column. So we should be fine with this. If we successfully added this name to the covered set, this was an uncovered value. Otherwise, this was already covered. And I believe that we have to report a useless arm here. And by the end, if we had no irrefutable value, and the covered set is not covering all the possibilities, then we have a case where we didn't cover every single value, and the complement of this covered set with respect to the ADT being matched here will give us the patterns that are essentially not covered. Now we need to extract somehow this. Just stash it away when we find it. What did we call this? Constructor being matched. And we have the ADT. This is essentially the reason why we stashed the ADT in the first place. Don't have the number of entries here, right? No, sadly, we can just add it. Of course, this could be null. I think there should be an edge case in the algorithm where this can be null, as in there were 0 rows. I am not 100% sure, but just for safety, I'll play it safe here and check for non-nullity. So we have uncovered cases and we need to report them. And we can even compute the uncovered cases, which is the constructor being match.adt to hash set. We turn it into a new set, and I think we can just subtract from it. I just don't remember the set operation. accept, I believe. Accept the width and the covered set, which will give us the set of uncovered names. Okay, and I believe that we are done here, and we should be able to construct our new decision tree node. Parent is going to be this instance. Arguments. I believe we didn't change any rows here, so they stay the same. The patterns, we just have a remaining patterns builder here. As for the actions, we have the same. Let's try this out. I believe that the result of the previous operation is being reused here, which is perfect. We can just continue this chain. And we're going to default by row 0, which is what I believe being defaulted by here. Let's see if we crash and burn. No, we do not. And the arguments should be the same, v0 and v1. So let's check that. No, it's just being v0. Oh, because we're specializing by none. It's easy fix. So the arguments are still just v0 because I'm stupid. I should have gone with something smarter here. We will have to deal with this. So the arguments are v.0 and v.1, okay. And the only action that should have remained is the second one, so action 2. Oops, this is correct. And there should be a single row where we have a discard and a 2. Indeed. Okay. Is there another example for discarding? Not for now. I guess we'll just take a leap of faith and hope that this is correct. Now there's a last thing that we need to implement, which is swapping. And fortunately, this one's pretty easy. We just take 2 column indices and swap the elements here. That one should be pretty easy to implement. As usual, I'll name it swapping because that's what the blog post calls it here. And the only thing that we need to care about is also swapping the arguments appropriately. That's it. So arguments will change, patterns will change, actions remain the same. What we could do is, well, what I'm going to do is pretty nasty. I'll do something like our swapped arguments is going to be this dot arguments. I think there's a to builder. Let's just call it arguments builder, I suppose. Does it have something like swap? Nope. You can definitely write swapping. hoping that C# supports this. Maybe it does not. We can't take the ref of these, right? Yeah, okay, then we're just going to do this. This is ugly, but we'll have to do. Hang on, we only need one array. We're not swapping around into arrays. And now we can just do this. Okay, that's arguments done. And now we just need to do this for each row of patterns. We can finally construct our next node. As usual, the parent is going to be this. The arguments, we have a builder for that. As for the patterns, we have a builder for that. And the actions didn't change anything. You can just inherit that. Okay, this looks fine. Let's see the sample in the blog post, which is conveniently enough uses the result of the previous operation to swap the two columns here. So let's do that. And what we should have is have the action swapped, and the pattern should be 2 and discard. Sorry, the arguments should be swapped. Did I screw up something? I might have made an infinite loop here. And I don't know how. Oh, yeah, I see. I screwed up. So the action should stay the same. Yep, we have the argument swapped, so let's hope that the patterns are swapped as well. Why is there 2 rows? Oh, what did I screw up here? Oh, because we need an empty builder here. Or rather, yeah, we need an empty builder here. What I wanted to do was like nested mutation, but it obviously wouldn't work here. So now it's fine, it's 2 and then discard. So yes, that's good. I believe with that we have implemented all 3 components of the algorithm. So we can do the algorithm finally. And let's just call it the algorithm. So the cases are the follows. If the pattern matrix is empty, that implies that it was produced by a defaulting operation that could find no row to include. So it is indicative of a matching failure. That's pretty easy. There are no rows. And we're just going to paste this here. Okay, it's simple enough. There's a second case. If the first row of the pattern matrix is irrefutable, meaning it matches everything, then matching has succeeded, and we return a leaf node containing a reference to the action vector entry for the first row. So we have essentially found a match. We can do this with a bit of link again. I'll leave it to do here as well. So, if there are other rows in the pattern matrix that are also irrefutable, then that implies the pattern corresponding to the first row subsumes them. In other words, those extra rows are redundant and they can be never reached. We can do that by doing something like so. And we just keep the first row, and then we take the ones where it's the same deal. All of the patterns in that row are essentially matching everything. And we should be doing something with them, but we won't bother. We are just laying out the skeleton of the algorithm. Now, if neither of the two previous cases hold, then we look for a column that contains at least one refutable entry. So we look for a column that has something that does not match everything. And if the found column is not the first one, we make it first by swapping. So this is where the swapping algorithm, the last thing we implemented, comes into play. Whoops. I'm just going to heavily comment this part of the algorithm. And by heavily commenting, I mean just copy pasting out the blog post. Because it's pretty well written. So, what we should do is somehow determine which column has an irrefutable, a refutable entry. For that, we could actually write a utility function. Again, it's not irrefutable, it's refutable. For me, the verb is very foreign. I'm not an English speaker. So, in my language, this would be a double negation thing, and it's hard to comprehend. everything here, then return this column. This is guaranteed to be the first one. And for safety, I'm going to throw an invalid operation and exception here, as I believe this should never happen. But we will see. I might be wrong. Did I call this correctly? First row, no, this should be first column. And if it's not the first one, then we swap it. Well, the swap should work unconditionally, but I believe for efficiency reasons this check is pretty cheap as well, so. Now that the first column is refutable, we collect a form of signature by analyzing each entry. If the column's type is a variant, then we collect all the names of constructors from entries that contain variant constructor patterns. For example, we would collect sum if we encounter sum1x. Similar collection is done for other kinds of refutable patterns, such as integer constants. Now, again, this is why we chose that we only include constructors here, because for us we can just look for type constructors. I'll just copy this entire thing here. I don't think there's any harm in over commenting this piece of code. It's not that it's complicated, but since I'm copying the blog post essentially word by word, I want to have the author's words exactly before I misquote him. I'll also include a comment here before people tell me I'm plagiarizing without giving credit, which I don't want to do. Okay, so we were here. So we know that the first column is refutable, which means that we collect the entries here. And we do that. Now, I don't know if here we want to care about... So, what I wonder here is that if the first row of the pattern matrix is irrefutable, do we care about the entire row or just the first pattern? What I believe is that we care about the entire row here. Okay, so we can collect the variants in the first row, and we can do that by selecting selecting the first column in each entry, or in each row rather. As I'm getting tired, I can speak coherently less and less, I'm sorry. And we check if these are constructors. And we collect, we can just leave them as is, maybe call a distinct by. So we only have it once. And I guess we can also just put them into an immutable array for easier debugging later. So we collected some, none, and such. Once the signatures are collected, a specialized matrix is produced for each one. Those matrices are then recursively compiled by the algorithm, and the resultant decision trees are recorded as targets of an n-way switching node in the decision tree. So this is where we make a decision in the decision tree actually, and specialize for the first column's variant types. So what we can do is go through each variant. And each variant is a constructor that we can specialize by. So here's where the specialization operation comes in. And well, yeah, we should record this as a child of this tree. If the signature is not complete, i.e. does not contain all potential constructors for a given type, then the default matrix is computed for the original matrix. The resultant decision tree is then included among the alternatives or the return switch node as the default case. Okay. So let me copy it here. So this is another child case. So in case the signature is not complete, which you can check by seeing if the variant's length is smaller than, well, the first variant. But we can just take the first variant and take its ADT and check its count. And in this case, we know we didn't cover each variant, so what we need to do is compute the default. And the observed column, the first one. And we need to record this as the default case. And we might actually be done. Oh my god, we might be done with this. So, the last thing that we can do is record the children, so we could actually visualize the tree. And what I'd love to do is, with each child association, we could actually specify why it was chosen as a child. You know, in this blog post here, they specialize why the hell the thing happened. So yeah, let's try to do that. Essentially, the parent we can just throw out, to be honest. We don't really need the parents here. So we can just record the children for everything. We might do something like a dictionary here. And we are going to specify with the key what's being switched on. So this is a failure, we don't care about that for now. This should be an action vector entry. Okay, we don't care about the leaves for now. These are going to form the leaves, but we're fine without them. So we're going to record this child, and this child is the default one, so and specialization is always recorded, defaulting is always recorded, and the one thing that we never record is swapping. We should record swapping, I believe. Yeah, because we just throw away the node as well. But what we could do is do something like target node is this. And make the target node the swapped one. And instead of this, from here, we're going to always use the target node. And what we can do here is that we did a swap. Then we can actually record that we have a child here for this. And I believe with that we have tracking for the thing. Now let's do a smoke test for the algorithm. Let's see if we crash and burn. We don't, which is awesome. But we can't see what happens, which is not that awesome. But what we could do is plot out the tree in dot graph format. What I usually do is Google a graph with visualizer online, something like this. And we're going to create a directed graph that could visualize us the tree. Now we don't need anything fancy. We just want to have these nodes, maybe even unnamed, and only label the edges. So what I'm going to do is create another public function. And I'm going to call it to.graph maybe. And this is going to be the thing that visualizes the tree for us in dot format. So I'm going to need a string builder. And I'm just going to call this graph G. We're going to have the end for it, and in between we need to declare sort of all the nodes of the tree. What we could do is give each node an index. So we could have an allocated set of names in a dictionary. And for each decision tree node, we assign a string maybe. And we could have a local function called allocate name. And that will take a node. Make the nullability analysis shut up. And if there's no such name, we are just going to allocate one. And we call this, I'll call it n, and then whatever the count is for node names currently. and we return the name here. Okay, this way we're able to allocate a name for each. Now, what we need to do is now traverse the graph with each node, through each node, and we can just write a local recursive method to do that. And what this is going to do is first we are going to append it to the list of nodes. I believe that that's legit in itself if we do this. And then we go through each child. And throw the label. Actually, this is a key value pair, right? So, yes, we have a reason in the key. So we're drawing one to the child, and we're going to label it. I hope this labeling syntax is correct. I don't usually remember dot correctly because I don't read it a lot. We usually just write it in the compiler as well. And we have a utility to do all this thing you see here, but obviously we're working outside that, so we have to implement it manually this time. And we're going to call traverse on the root, which is this. Okay, I think that's it. So let's try to visualize our graph. Okay, we obviously have no new lines, which is easy to fix. We just need left underline. And the graph does look a bit too small to be correct. Let me visualize it on another screen for you guys. So this is our graph currently. Now, if we compare it to what it should be for the sum none example that we still have here, the sum and none constructions are fine actually. But within the sum construction here, we should have a constant 1 and the default selected out. So we are screwing up in the first step of the algorithm. Let's check it. So we're in the root. And within the root, we have all the 3 patterns and all 3 actions. And in that, we check the first column with a refutable value, and that is going to be the first column. So we don't swap. We collect all the variants, which should be sum and none. Indeed. Now, we specialize for sum, and that should be what we expect. Oh, I think I do know what we forgot. I believe that this needs to be recursive. So, okay, we collected out each child, but then each child needs to have the algorithm invoked, because these are the base cases. So, Let's see if we explode now. We definitely could because we have recursion. Yes. Item with the same key has already been added. Oh, I'm sorry. We don't want to go through this children, but the target node's children. Because there's a chance we swap here. And now we have actually the Stack Overflow. Okay. And we did that in Specialization. Okay. Let's try to step through this because the example isn't too big. So we select out the two variants. And we specialize to sum. And this looks fine. And then we specialize to none. And to me this also looks fine. And I believe that we covered everything, so we shouldn't hit that, yes. And then for each child, the first child is going to be the sum case. We are going further in, and what should be happening, let's see, is indeed we should select out a refutable value of 1. So we should have it in the first column, indeed. And we should select out only 1, okay. And the specialization of this is only the first row, so specializing this should be x and 1. So for some reason the first column disappeared. Well, of course, because we removed the remainder there because it's a null array. So let's see what we have there. Yeah, it's just the remaining variable here. Okay, that's good. And we should also default here. And we have quite a few more default values, so I can't really check what happens with the defaulting here. But it's a discard and a 2, which actually looks fine. Okay. Let's look at the children. And the first child is going to be this left one. Good. So this should actually hit the end of the recursion because it matches everything. Indeed. So we're done here. And now we just have the other child, which is the one with action 2 here, which should be a discard and then the constructor for 2. Let's check that. Indeed, we go into that, and what should happen is we should be swapping. And indeed, we are going to swap. Let's check. Okay, the 2 gets there. And then we should pick out 2 as the sole variant here. And indeed we do. And we should have a 2 and the default case picked out for us. So we're going to specialize by 2, which means that we should only have a discard and a 2 here. So the action should be 2, that's correct. And we should only have a discard now, which is also correct. And now we should notice that there's supposed to be a default. And this is the case where I believe we could be screwing up, because the default should be a failure here. I don't know what will happen here. Okay, we have a bunch of uncovered cases, that's good. Now we should be correct because we removed the 2. And why are we not failing here when constructing the default? So I believe that we screwed up is the defaulting. So let's quickly read up. Oh, when the matching is inexhaustive, defaulting creates an empty pattern matrix. Oof. So yeah, what I should have done here is this. And let me just copy it here. So that's pretty simple. This is just an empty mutable array. This is also an empty mutable array. Yet another immutable array. Let's try now and hope we do not recurse infinitely. We terminated, good, but we stopped way too early, which is not so good. And since the only thing that we changed is defaulting, let's take a look again. In case where the matching is inexhaustive, default creates an empty pattern matrix. So apparently we are doing that in the sum case as well, which is not good. For some reason we are stopping here. wonder why we get into this case in the first place. So when we default the first one, which is the 2 underscore, oh, that's actually a failure. That's good. That's good. Okay, that's fine. Okay, let's try to run the algorithm from top to bottom again. So initially we should dissect to some and none, which is correct. And we should be having 2 children. The first one with key sum and value of 2 patterns, which is correct. It's this one. And we were exhaustive here. So then we recurse and we hit the first child here, which is this one. And let's recurse here. Let's see what happens. So what should be happening is that we should pick the first column because it is a refutable value, and indeed we do. And we collect out just 1. And we should specialize to it. And that's what we do. And with that we should have a singular pattern with a wildcard. And it is that's the case. And we add it as a child. Okay. And here we actually should have a defaulting case. With 2 patterns, indeed, that's correct. So that's already more nodes than what we are printing. So what I believe is that now we're screwing up something simpler. Maybe the traversal somewhere. Of course, we don't traverse the children. Oh crap. Oh no. My Visual Studio is very much not happy. We might crash actually. Dang it. I'll try to kill it. Just a second. But my Visual Studio is very not happy. Okay. Let's try it again. So why are you not happy when I call traverse on child? Do we have any circularity in the tree maybe? We shouldn't. We really shouldn't. Let's take a look. Okay, so this one has 2 children, that's expected. This one also has 2 children, so if we recurse here, 2 children, 2 children, and this shouldn't have any children at all now. And still it has 2, so that makes me believe that we did some recursion thingy. And let's see where this children is referenced. So here we're adding the target node, which is not this. Swapping always returns a new node. Yes, okay. Then we're adding a specialized thing to target node, and then we're adding a defaulted value to target node. Well, what we could do is create a helper. Okay, let me find the references again, and we're going to replace this with that child. Same thing. Same thing. Let's do another check. Okay, now all the references are observing. Let's see. Nope, this is unfortunately still a recursion, so it's probably something messier. What we could do is I'm going to track that, and if that is greater than like 8, we're immediately returning. And this way we'll actually have a finite tree to visualize. Let's see. Oh my god. This is massive. This is absolutely massive. And to me it looks like there's a cycle here immediately. Oh my, let's reduce the depth. Let's do something like 3, maybe that's more reasonable. Okay, that's definitely a smaller graph. Let's try to visualize it. With the browser not appearing. Oh, it disappeared into the 4th window that I rarely use. Or 4th screen, sorry. Okay, so there's some back and forth here for some reason. When we're approaching N2, we're cycling back to the parent. And we're also cycling to ourselves, which I do not understand why we are not yelling here then. Did I just make a very stupid mistake in the traversal itself? I don't immediately see anything wrong with the traversal. the sibling nodes shouldn't really connect to each other. I assume these are the top level siblings. And these are just pointing to each other like crazy, which is weird. And what is weirder is that they even have the reason code that they were specialized into their sibling. This isn't adding it to the children, right? Nope. This is just creating unfortunately, this does look correct. Since we're only doing specialization here, I could maybe put a breakpoint here. But we're only doing a couple. Heck, I think we're only doing the correct amount because we do 1, 2, 3, 4 specializations, and this is 1, 2, 3, 4, done. Which means we must be incorrectly checking the children somehow, or tracking them rather. Maybe it's the swapping. No, it's not. I don't think it's the swapping. But there's no mutation here apart from tracking the children. So we're specializing once with some, once with none, once with 1, and once with 2. Some, none, 1, and 2. So that's perfect. I honestly believe that we have implemented the algorithm correctly. And now we are just screwing up something so ridiculously simple. this is currently the top level, and with the reason sum we want to append probably this, so the 2 by 2 matrix. Let's check if it is the 2 by 2 matrix. It looks like so, yeah. Okay, next. This is again the root. So we're probably adding the none variant with the discard. And indeed we are. So next we are adding 1. So this should be the 1 discard, discard 2. This is 1 discard and this is discard 2, yes. And we should be adding discard. And indeed we are. So next we want to add a default, and it's going to be probably adding it to the 1 discard, discard 2, and we are going to add the discard 2 to it. Yes, this is the case. So next we are swapping, and we are probably swapping the discard 2 to get a 2 discard. Discard 2 to get a 2 discard, indeed. And finally we should have a 2 and the default added. Now the 2 should be added to 2 discard, yes. And we should be adding a discard only to it. Yes. And the last one should be default. And we're adding a failure to it, which means that there are no patterns in this node. And indeed there are none. And we're done. So we could be screwing up name allocation. At this point, I am really not sure. I believe I'm doing this correctly. Maybe I'm not, who knows. So node names decision tree node to string. Decision tree node is a class, so it has reference semantics. If we are able to get not able to get a value, then we are creating the name and we are adding it, so next time we don't run into this. Okay, that's fine, that looks fine. Traversal, shouldn't need this crap. So first we are printing the node name here. Then we are going through each child of this thing, and we are drawing a line from the node to the child. And then we also traverse the child. That looks correct to me. And then we're traversing the root. But for some reason, the children gets messed up. Let's actually do this. Let's see how many children this has. This is 2 children. And this has 2 children. And this is no children, so this is correct. So 2 children, and none. So left, right should be 1 child and then 2 children. So let's go left, right. This is 1 child, and this is 2 children, and the left of that should have none, and the right of it should have none as well. Good. So the only remaining part in this subtree is the right side, which should have no children at all currently. Indeed. So I am claiming bullshit. So we're traversing over this. We are allocating it a name. And it's getting n0, that's fine. And we're adding it to the node names. Now we have a sum and its child. Now n0 already had a node name. N1 will have a node name allocated. And we can append n0 to n1, and then we're traversing the child, which should be the left side here. This one. 1x, 2y, so 1 discard and discard 2. And that is the case, yes. Okay, this already should have a name allocated, it's n1. And it should have 2 children, 1, and the default. No. Oh, I'm an idiot. I'm an idiot. This is all we messed up so far. This. It should not have been a this. It should be always be the actual node that we're traversing. Oh, damn it, that is such a stupid mistake. And we spent such a long time debugging nothing but the traversal. Let's see. Now, I believe this is correct. I'll try to fit both on one screen so we can compare the structure. What I'll do is I'll grab a screenshot and put it in Paint because I can't seem to zoom out on that other page. Okay. So from the root we have a sum and a none case, and from that we have a 1 and a default. Then we swap here, and then we have a 2 and a default. Again, we don't really care about the leaves for now. And on the other side we just have a none case, and that's it. Alright, with that I claim that the algorithm should work. Maybe we could try another example from the site. Okay, let's try this one. So this looks like a constructor pattern for a list. Let me copy it on from my other screen. So for this we just need a list type, which is an ADT of a cons and a nil. And so I like this pattern a lot for testing, so I'm just going to comment it out. And we need to construct a pair here actually. So yeah, we actually need another one called a pair, I believe, because our initial match only allows for a single pattern, but maybe we can actually live to that. We could actually lift that constraint for now. So we could call it patterns here, call it patterns. And where else do we have a problem here? This is fine. This is already kind of ready to accept it. Well, yeah, the construction of arms will be a lot uglier from now on. And what we need is a nil. First case, as you can see here, and we also need a discard as the second. The second arm is the same thing but symmetric. Maybe delete it. Oh yeah, I could just swap these two. Oh, and now that we have the same patterns here, doesn't really care. And the last one should be constructing cons of two discards. And here I will actually need to specify pattern. And I believe, yes, we just do the same thing again. This is going to be case 3. We have an index out of range. Did I screw something up? A list of patterns here. It's 2 patterns here. And it's 2 patterns here. Should be 2 patterns here, and cons is always 3 arguments. Let's see where we are crashing actually. That could give us a hint. So we're swapping column 0 with column 2. And oh, okay. I'm just an idiot. I should have specified 2 inputs here. Okay, let's plop this into the visualizer. And again, I'm going to copy this out for you on Paint. And let's bring the sample into view. And they don't look the same. Wait, they do look the same. I just looked at the wrong sample. So, wait, no. This is the one I should be looking at, and this is what we're getting, I believe. So the left side is nil, then it's cons, and for some reason it does a swap here. Did I mess up by any chance? the example. Let me check. So the first one is a nil and a discard. That looks correct. Then it's a discard and a nil. And then it's a cons of discard, discard, and a cons of discard, discard. So it looks correct on first glance. Now let's check the other sample if it still works. Maybe we messed up something since then. Obviously this won't be happy. Whoops, I pressed caps lock. So let me copy this out because we don't need it. And let's check if this still has the same shape as it's supposed to. Where do I have the visualizer? Chrome keeps putting it to the wrong place. So let's check the blog. So we have a sum of a 1, yes, then a default, a swap, a 2, a default, and a none case. Okay, so this looks fine. Why is this one not working? Now let's see if ours is even correct before realizing that this is just a slightly different variation of the same algorithm. Let's check what ours produces. So we're checking the nil, and if the first one is a nil, we should be done. Yeah, we know from that we are on the that we are on case 1 essentially. Now in case of cons, we do a swap here. And that is because we only have, wait, so only cons remains. I wonder why we swap there. Oh, I know, because only the discard nil and the cons stays there. So if you look at the last two cases, it's discard nil and then cons. So when we choose nil here, the remaining ones are discard nil and then cons. But why the hell are we swapping? We shouldn't be swapping here. Let's take a look. When we invoke swap in this sample, why we do that. So, because we found the first column with a refutable value at column 2. Now where the hell are we even? Which node is this? We only have a single pattern and it's a discard cons. Yeah, so it's when we exploded this last case, I believe. So it's discard, discard, and then this last case. Okay, I mean, that's not unreasonable here. So that's why we're getting a swap there. And then, in case of cons, we're essentially done because we have a case here. And in any other case, I think that this is incomplete. So yeah, if first one is nil, we have case 1. And in case the first one is cons, well, no, because in that case, if we choose cons here, we should still have the second one as nil. So what I believe is that we're discarding a match arm here for some reason when specializing to cons. Or rather, when we are specializing to nil, maybe we should include the match all patterns, like this card. I believe that what we are not handling properly is what to do with this row, for example. I believe that this gets discarded immediately. And that's a problem, I believe. So if we go to the first iteration of the algorithm, we obviously collect the two variants nil and cons. Cool. And for nil, we get a specialized with a single pattern, which is expected. If we have nil, then anything can be on the other side. And then we have cons. And that specialized only gives us the anything, and then a cons. So what we're missing is handling rows where the first value here, the first column of the row is irrefutable. I'm not sure if we have that specified anywhere what to do with that. I'm reading up on this, just so you know. Yeah, so I believe I am missing what to do with this line, to be honest. So like, what to do with this? I'm not 100% sure what to do with them currently. So I understand what we're not handling here. And this is the fact that we're discarding, where's the sample? So we are discarding this arm completely, which throws the algorithm completely off. But I am not entirely sure what to do with this, where this should be included. Now here, it somehow lands in the specialized cons case. So maybe specialization should include more than just constructor patterns, but maybe match all patterns as well. So we could try that out pretty easily if we say that if row 0 matches everything for this. But to me, that would sound like it would have to leak into this case. Maybe it does not, I'm not sure. Oh, so we cannot do this, right? Because we need a constructor and we need to check its name as well. If we do something like, whoops. We could definitely try this. Maybe it's what we were missing. Okay, let's check the resulting graph. Interesting, but it could be correct. Let's put them near each other. Oh, I can actually do it like so. Okay, so we have a nil and a cons. Then we do a swap. Maybe this notation doesn't do it anymore. Then we have a nil. Then we have a default case, a swap, then a cons, and a default case. So structurally, this actually looks fine. Now, what I want to check out if that we ruined the other test case. So it could be that they are just using some more terse notation, like they are not recording each operation in that more compact example. Now let's see here if I can put them near each other. Yes. So some and none. For some we have a 1, a default, a swap, and a 2, and we have a none. Okay, so I believe that we have cracked what was wrong. So to recap, the part was wrong was that when we specialized, then we didn't consider rows that didn't match by a constructor name, but essentially matched everything. So we need to include that. And it sort of makes sense now that we think about it. So it's been a pretty long stream and I'm pretty tired, so I think that we're gonna end it off here. I believe that this algorithm is now at least mostly correct. we tested the whole 2 cases, but maybe tomorrow we can do a quick stream where we improve it. Maybe we visualize which case we ended up with, which is pretty important. Also, we could make a way to compact the tree. So for example, on swapping or defaulting, we do not explicitly annotate those operations. So we could compact the tree like this. We could also try out this example, this sum none example, or maybe even encode this red-black tree algorithm and somehow try to compare the tree. Alright, so thank you everyone for watching. If there are questions, feel free to ask them in the chat. I'll get back to them probably tomorrow in the follow-up stream. I hope this was somewhat interesting. It was for me. It was definitely a learning experience to see this algorithm in action and to actually comprehend what it's doing. And I hope I gave you some fun insights how one would approach implementing an algorithm that they never have written before. So again, thank you everyone for watching. Bye bye.